All right, everyone, Mr. Graham here. Today I want to start going over or start discussing how you can go about solving kinematics problems algebraically, not graphically. And I want to review a couple topics first, a couple things that we need to know before we can actually start using the kinematic equations. And so the topic is acceleration in kinematics. Remember, kinematics only refers to uniformly accelerated motion, so I like to think of that as UAM. Some things we need to know: the distance that an object travels. It's just the total distance, regardless of the direction it goes, regardless of whether it reverses direction. The distance that an object travels is literally just the total distance an object travels. The displacement, though, is the distance the object is from its starting point, or any point in that's important. From the start of its motion, we measure its displacement from that point. And it doesn't matter if it's in the positive or negative direction. It doesn't matter if it reverses direction. It's just the distance that the object is from where it started. And it is a vector, and so it's points from where it started to where it ended. The acceleration of an object is just the rate at which its velocity changes. We typically think of acceleration as speeding up. When most people that don't know physics talk about acceleration, they think it means speeding up, but it also means slowing down or actually reversing direction. Right. All right. Speaking of acceleration, it is a vector quantity, so it has a direction. Which means its direction matters. I'm sorry. Okay. Positive acceleration means that your velocity is becoming more positive. That means if you're moving in the negative direction, that actually means you're slowing down. So it could either mean speeding up or turning towards the positive direction, or slowing down while traveling in the negative direction. The easiest way to think about that is just if the velocity and the acceleration are in the same direction, the object's speeding up. If they're in opposite directions, the object is slowing down, regardless of which one's pointing in the positive or negative direction. Negative acceleration, it is sometimes called deceleration, but I would caution you to stop using that word, at least whenever you're talking physics. When you're doing your physics, we don't really use the word deceleration, but just because it's used so ubiquitously in common language, just understand that people will say that, but from a physics standpoint, an acceleration is any change in velocity, even if it's slowing down. So it could either mean slowing down or turning toward the negative direction, or speeding up in the negative direction. Again, the way to simplify all those two bullet points is just if the velocity and acceleration point in the same direction, the object speeds up. If they point in the opposite direction, the object slows down. It is measured in meters per second, essentially how fast you get fast or how fast you get slow. Or meters per second squared is usually how it's written. And so the formula for acceleration, the mathematical definition is just the change in velocity over time. Okay. And you can actually solve this if you expand delta V out to V final minus V initial. You can expand that and solve for V final, and that's actually kinematic equation number 1. We saw how we can get that equation from the analysis of the velocity time graphs, but you can also get it from just the definition of acceleration. The unit for acceleration is meters per second, but we usually don't write it like that. If we solve this using our algebra, we make a fraction out of that bottom denominator. You can put it over 1, and then you just multiply by the reciprocal, and what you get when you do that is meters per second squared. Okay, so this is the unit that we label accelerations with, but it does mean meters per second per second. All right, the 3 kinematic equations. These are on your formula sheet. You don't have to memorize them, but you're going to use them so much probably that you'll end up memorizing them. Kinematic equation number 1 says final velocity in the x direction equals initial velocity in the x direction times time plus, I'm wrong. Sorry about that. Should be looking at my formula sheet when I do this. It is the initial velocity in the x direction plus the acceleration in the x direction times time. And remember, these subscripts just tell you the direction. When we deal with free fall, we will then be changing to the y direction, but for now we're just dealing with horizontal motion. Kinematic equation number 2 says final position equals initial position plus the initial velocity in the x direction times time plus 1/2 times the acceleration in the x direction times the time squared. And kinematic equation number 3 is final velocity in the x direction squared equals the initial velocity in the x direction squared plus 2 times the acceleration in the x direction times the time, the final position minus the initial position. And watch the video from yesterday when we derived these equations. Note that you can subtract delta x naught. You can subtract initial position from both sides here and get delta x on the left side. This can obviously be rewritten as delta x, but this is the form that the equations take on your formula sheet. All right. So let's actually solve some problems. First, let's make sure we understand what our kinematic variables are. Just v with no subscript is our final velocity. V naught is our initial velocity. Remember that naught just signifies that the initial time is 0. It's assumed to be 0, and so that's where that 0 comes from. So the velocity at time 0, this is the velocity at any later time. Our displacement is delta x, and remember that when we're talking displacement, we're talking about positions. So x naught is our initial position. Sorry, I'm not writing this very well, but our initial position, and then just x by itself is our final position. Okay, our acceleration in the x direction is a with a subscript x, and our time is t. Again, those subscripts, I talked about it yesterday, the x subscripts, if we're talking velocities in the x direction and accelerations in the x direction, you can drop those if you know for sure that you're dealing with motion in the horizontal direction. All right, so we're going to go ahead and solve some example problems here using what we call the guess method, and I'll talk about the guess method as we go through this. The guess method, just each letter here stands for a certain variable. The first letter, G, stands for your givens. So I'm going to list my givens here first. So a car driving at 25 meters per second slams on the brakes and slows to a stop. So that gives me some information here. Before I even read the rest, I'm gonna go ahead and write down that information that's given to me. I'm driving with an initial velocity, v. I'll go ahead and use these subscripts in this particular problem. Our initial velocity is going to be 25 meters per second. I really recommend you do it like this. Write the variable, equals, write the value, write the units. It just gets you used to doing all this stuff. And it slows to a stop. Notice it slows to a stop. If you slow to a stop, then your final velocity in the x direction will just be 0. So that goes in my list here. 0. In 3.6 seconds, well, that's obviously a time, so my time is 3.6 seconds. What is the car's acceleration? So we are looking for the acceleration in the x direction. That is actually, that's what the U stands for. The U stands for unknown. G is given, U is unknown. The E stands for equation. And I like putting my givens and my unknown in a nice vertical list like this, because then you just have to find the kinematic equation that matches those variables. So if I go to my kinematic equations, I see initial and final velocity, time and acceleration. Well, that's going to be kinematic equation number 1. So I'm going to write the equation first. Always write the equation first. You're going to do an AP exam. If you don't write the equation first, it's very likely you're going to get points off. Very often you get awarded points just for writing the correct equation. So I'm going to require that when you solve problems, you write the equation first. Don't start by just plugging in numbers. You will lose points both in the class and on the AP exam. So I've chosen the right equation, E. The first S stands for solve. So I need to solve this equation for my unknown. Okay. I'm looking for the acceleration, so that means I need to solve this equation to get the acceleration by itself. So to start that process, I'm going to use reverse PEMDAS. I'm going to subtract the initial velocity from both sides. And so when I do that, I get on the left side, final velocity minus initial velocity equals, on the right side, I have the acceleration times time. And then to get the acceleration by itself, I just need to divide both sides by the time t. And when I do that, I get that my acceleration, which is by itself now, I'm going to put it on the left. I like putting what I'm solving for on the left, is going to equal final velocity minus initial velocity divided by time. And our last S stands for substitute. So now I'm going to substitute the numbers in for the variables. In on-level and pre-AP, we let our students substitute first and then solve. In AP Physics 1, you can't do that. You got to solve the equation first for the unknown, and that is because on the AP exam, once you know physics well enough, you actually will not, or many problems the answers will actually be equations themselves. You won't even have numbers to plug in. But if you have numbers, which we will when we're starting to learn about this stuff, that's where we substitute our numbers in. So our acceleration is going to be final velocity, which is 0 meters per second, minus my initial velocity, which is 25 meters per second, divided by the time. The time was 3.6 seconds. Let me grab my calculator. And so I'm going to have 0 minus 25 meters per second, which is negative 25, and then I divide that by 3.6 seconds. And so I get an acceleration of negative 6.94 meters per second squared. I typically round to 3 digits. On the AP exam, if you round to 3 digits, if there's a numerical answer, that's usually fine. Please box your answers. Box your answers. The AP exam readers expect you to, and so I will expect you to as well. They won't be checking sig figs though, so 3 digits, leave your answers in 3 digits and you'll be fine. So notice what I did there. I'm going to go ahead and make a little table here. I got G is our given. I listed out my givens. The U is identify your unknown. Sometimes there's more than one, but for now it's just going to be one. You pick the right equation. You solve for the indicated variable. You solve for your unknown variable. And then at the very end, you substitute in your values. Okay. Nice methodical way of going about this. If you have a natural affinity to physics and you don't need to do that, that's okay. But most people, I'd say 95% of people don't. And when I solve these problems, I do it this way as well. So I pretty much expect you to, unless you're a super genius, which you might be. But if you're not using the guess method and you're not doing well in the class, you're just making it more difficult on yourself. I'll tell you right now, students that don't use the guess method don't tend to do very well in the class and on the exam. All right, let's try another one. Bob starts at rest. I'm going to stop right there. Bob starts at rest. Initial velocity is 0. And runs with a constant positive acceleration of 4.5 meters per second. So that gives us our acceleration, meters per second squared, 4.5 meters per second squared. What is Bob's velocity when he is 52 meters from where he started? So 52 meters, there's a couple ways we can write this. We can write delta x equals 52 meters. However, realize that delta x is not in our formula sheet. So another way we can write that is that our initial position we just assume to be 0 meters, and our final position is then at 52 meters. If you're running a race, you start at the 0 mark, and then you end at the 52 mark, and then your displacement will be 52 meters from the 0 meter mark, okay? So I'm going to kind of cross this guy out so that it matches my equations, but hopefully you understand how that works. And we're looking for his final velocity. What is his velocity in the x direction after he undergoes that motion? So that is our unknown. Then we pick the right equation. And again, I have this list, and I just look at my list to see which equation has those variables. So I have the 2 velocities, I have the 2 positions and acceleration. And so that is kinematic equation number 3. So the equation here is going to be final velocity in the x direction equals the initial velocity in the x direction squared. Sorry, both of those are squared. Plus 2 times the acceleration in the x direction times final position minus initial position. And when I know things are going to be 0, if I know some of these quantities are 0, I go ahead and just get rid of them immediately. So I know my initial velocity is 0, so I can say that that's 0. I know my initial position is 0, so I can say that that's 0, and then rewrite the equation, the simplified version. It just makes the math a little easier. So 2 times the acceleration times the final position, x. And we're looking for the final velocity. It's almost solved for, but it is squared. So what we're going to have to do here to solve for our variable in question, we need to take the square root of both sides. The square root of final velocity squared is just final velocity. That's going to be the square root of 2 times the acceleration times the final position. Now that I've done that, now I can substitute in my values. So my final velocity is going to be equal to the square root of 2 times the acceleration, which is 4.5 meters per second squared, times my final position, which is 52. And when I solve that, I'm going to just plug that in my calculator. I'm going to do what's under the radical first. If you have a different calculator, it'll be a different way. You can put this in a little more visually appealingly. Sorry, I don't think that's proper grammar, but whatever, I'm a science teacher. So 2 times 4.5 times 52. So that's what's under the radical, and then I just take the square root of that. So I get a final velocity of 21.6 meters per second. Bob is very fast. If that's a running speed, that is incredibly fast. Don't think that's actually possible, but who knows? Okay, another Another example problem, I'm going to go ahead and drop the X subscripts just so you can see what it looks like when you do that. I'm just, again, assuming that I'm traveling in the horizontal direction. Cars that accelerate typically are traveling horizontally. So a car begins to accelerate at 5 meters per second squared. So 5 meters per second squared. So that's my acceleration, sorry. Oh, a car at rest. Well, let me write the acceleration. Sorry, I said I was going to drop the subscripts. Let me start that over. A car at rest. So at rest means my initial velocity v naught is going to be 0. Accelerates at 5 meters per second squared. So my acceleration is 5 meters per second squared. How long will it take for the car to travel 300 meters? Again, travel 300 meters, that's a displacement. And so I'm going to assume my initial position is 0 and my final position is that 300 meter mark. Say this car's having a race. And then my unknown, it says how long will it take for that to happen? So time then is my question mark. Now I got to pick the right equation. Again, if you do it this way, you just got to pick the equation that matches all those things. So what equation has the initial final positions, the initial velocity, the time, and the acceleration? Well, that's kinematic equation number 2. So kinematic equation number 2 says final position equals initial position plus the initial velocity times time plus 1/2 times the acceleration times the time squared. Again, I like crossing out things that I know are 0. So I know the initial position is 0. The initial velocity is 0. So it doesn't matter what the time is. The initial velocity is 0. This whole term is 0. Doesn't matter. It could be a billion seconds. Billion times 0 is still 0. And so the simplified equation is simply final position equals 1/2 times the acceleration times the time squared. We are asked to solve for the time, so we need to get everything else on the other side. So my first step, because I don't like fractions, and if I can get rid of them, I do. Multiply both sides by 2. I got a numerator 2 and a denominator 2 on the right side, so those cancel. On the left side, I have 2 times the final position. On the right side, I have the acceleration times the time squared. I'm going to divide both sides by a, because I need to get t by itself. Numerator a, denominator a, they cancel. So next step, I have 2x divided by the acceleration equals the time squared. And then to get t by itself, I just have to, again, square root both sides. And so when I do that, the time is now just the time. The square root of time squared is time. And then I have, on the other side, it's going to be the square root of 2 times the final position divided by the acceleration. And so the time is going to be equal to, this is my final, I'm now substituting. Again, on the AP exam, very often, your answer will be the equation. Very often, answers on the exam will be the equations, because that's really the important part to be able to solve these equations like that. So that time is going to be 2, the square root of 2 times our final position, which is 300 meters, divided by the acceleration, which is 5 meters per second squared. And then I just grab my calculator. I'm going to do what's under the radical first in my calculator. It's 2 times 300. And then I divide that by 5. And then I take the square root of that. And then I'm going to round that to 3 digits. So my time is approximately, if I round this to 3 digits, then that 9 rounds up 1. And so this will actually be 11.0 seconds if I write that rounded to 3 digits. Okay. All right, let's do one more. A car speeds along at 27 meters per second and then slams on its brakes. So that tells me that it's starting with an initial velocity of 27 meters per second. Slams on its brakes. If it takes her 4.8 seconds to skid to a stop, well, that means if we stop, our final velocity then is going to be 0. And if the time takes at 4.8 seconds, how far will the car skid? So how far? Again, we can say that's like delta x is going to be our question mark. We could say that. But again, I'm going to assume that our initial position is 0 because that's where the motion that we're interested in starts. And our final position will be our question mark. Okay. And again, I just look for an equation, a kinematic equation that has all those variables, the 2 velocities, the 2 positions, and the time. So again, we're going to be using kinematic equation number 3. Which says that the final velocity squared equals the initial velocity squared plus 2, this is the equation. I forgot to write my unknown too. Plus 2 times the acceleration times final minus initial positions. Okay? And then I got some zeros here to make my life a little easier. The final velocity is 0. My initial position is 0. And so this equation actually becomes 0 equals the initial velocity squared plus 2 times the acceleration times that final position. And what we're looking for is x here. So I'm going to first get v naught squared to the other side. Remember, I'm doing reverse PEMDAS here. So on the left side, I have negative v naught squared. And that's going to equal on the right side, I have 2 times the acceleration times the final position. And then to get x by itself, I just divide by 2a. And I do that because now I have a numerator 2a, a denominator 2a. So x is now by itself. Oh, that is my solving. I'm solving now. And then I substitute my values at the very end. And since x is now by itself, that's going to be negative v naught squared over 2a. Then I'm just going to substitute in the values. So that's going to be negative my initial velocity, which is 27 squared. Now this negative here doesn't get squared, right? That doesn't get squared. Over here, v naught squared, we would put in a number for v naught if we knew it, and it gets squared. And then we subtract it to this side. So that negative is not inside the parentheses. So if you were to actually square that and make this a positive value, your answer would definitely be incorrect. Okay. Oh, I picked the wrong kinematic equation, didn't I? You guys see what I did wrong here? Time function. I messed that up. Sorry, guys. I'm gonna go ahead and make another video for this one. Sorry about that. See, even physics teachers get these wrong. Sorry about that.